I think it might be worth, since we began by discussing Einstein a bit, talking a bit about gravitational lensing and Eddington and what this phenomena is and how it was related to relativity and
Yeah,
then
it's another
discovered.
wonderful story. It was 1919, I think, when Eddington um, led an expedition to witness an eclipse. And it was a total solar eclipse, which is just a very lucky accident that our moon happens to subtend the right size on the sky to completely occult our sun. That's just an accident. And in some very large number of years, it will spiral away from us a little bit and no longer be the case. So we'll no longer be total solar eclipses. So we joke, like, you have to do astronomy now, now's the time, seize the day. So this total solar eclipse was very noteworthy to Eddington, one of the very early proponents of relativity, because it allowed him to make a very unusual measurement. He was looking at a star cluster that technically was behind the sun. Now, if the sun is blazing bright, you can't directly look through the blazing sunshine of the sun.
It's pretty bright.
It's pretty bright, this little star cluster. But if the moon helpfully occludes all of the starlight of the sun, you can see faint objects around the sun. Now, if relativity is right, the light traveling from the star cluster, some of it will go above the sun and around the sun because of the bending of the path of the light. The light won't just travel straight out like straight rays. It will actually follow curved paths around the sun into your telescope so that to you, it looks like the star cluster has repositioned somewhere where it is not. And in other words, you're seeing behind the sun. And how are you seeing, if you make this observation, you're technically seeing something that is behind the sun. And how is that possible? It's possible because the path that the light follows is curved. And so Eddington set out this expedition. I believe he had a team in Brazil, and his team that he was with was off the coast of an island in Africa. And solar eclipses only last a few minutes. And initially there was rain and cloud cover, but a couple minutes into the eclipse, it breaks. They make this observation. They can see the star cluster. It's popped out magically from behind the sun, confirming Einstein's prediction of the bending of the path of light. There's some debate among historians of science how good the data was and how hopeful he was to make the observation. But the lesson is there that it was the first confirmed observation of Einstein's theory of curved spacetime, and it catapulted Einstein's fame in the English-speaking world. I also should say it was also a profound moment of a transcending nationalism and war, because this is just 6 months after the end of World War I, and Europe is decimated, and the British and the Germans, of course, were in this terrible conflict. And for an English scientist to confirm a German scientist's work was quite radical in its way. It was like quite a statement for him to do that. So Einstein becomes front page news, and it really marks a transition scientifically and I think culturally. Sometimes joke like they stepped out of the shadow of the war into the shadow of the moon.
That's interesting.
And and emerged as like cooperative citizens of the same Earth.
Yeah, I imagine that must have been such a remarkable moment to realize that experiment confirmed theory and showed that we lived in a radically different world than people had realized before Einstein.
Yeah, absolutely. And a much more radical picture than even Einstein realized. Einstein did not solve his equations to find the black hole. We just discussed that was found by somebody else. And he didn't solve his own equations to find the Big Bang. That was also found by other groups. And he was quite resistant to both of the ideas, not the math, but that nature would have such things in it. He resisted that interpretation. And of course, black holes are very much part of our reality, our astrophysical reality. We observe them. They're there. They're They're part of the functioning of our galaxy and the space that we live in.
And just to make sure that I have what was happening clear for our audience, the mass of the sun is sufficient that it is curving space, and then light is traveling following a geodesic, I think, so the shortest possible path between 2 points, and it arcs around the sun, traveling from behind it toward the viewer.
Yep, exactly. And the sun is not dense enough to create an event horizon. So the light escapes and it comes at us and it hits our telescope, but it's still a curved path. And if the sun were to collapse and get denser and denser, the path that the nearest light that's just barely skimming past the star will get tighter and tighter, and eventually you'll even find a circular orbit for the light, and when it gets small enough, the event horizon. So our sun's like 1.5 million kilometers across. If we wanted it to be a black hole, we'd have to make it 6 kilometers across, and that's where the event horizon would form. So it's a pretty radical compression. And it won't happen to our sun. Our sun will have a different death state in its future than the black hole.
You just said something that, I mean, all of this is very fascinating, but something particularly fascinating. Are you suggesting that just as the International Space Station orbits around the Earth, that there is light that is just sort of trapped in an orbit around black holes? It's just going and going?
Yeah, you can... just like they had to compute where's a good circular orbit for the International Space Station, to be on them, you can ask, are there any circular orbits for light itself? And there is one around every black hole just outside the event horizon, like just outside the event horizon. So when you start getting light so sharply curved, the path so sharply curved that you're making a circle, the event horizon's imminent. It's just inside that region. So I think it's like 3 times. So let's say, maybe like a radius of like 6 kilometers out, or so 12 kilometers across. That can be a circular orbit for a black hole sun. If it was our sun, it would be about 12 kilometers diameter, and the event horizon 6 kilometers. So they're really close to each other. You're talking about fitting inside Central Park, but so if you were to try to as you pass that orbit, you could shine a light beam and it would go around, bounce off the back of your head, and then come back to your eyes, and you could see the back of your head.
Well, I know I'm getting a little bit ahead of myself here, but I just have a bit of a clarificatory question. So the radius of a black hole is directly connected to that black hole's mass. And because black holes are constantly accreting mass, the event horizon is consequently changing at all times. Does that mean that while in theory, if you had a black hole that remained of stable mass, there weren't quantum fluctuations around the event horizon, we might see light traveling around it indefinitely, but because
it's delicate, it's hard to get it there.
Yeah.
I'll let you finish your question.
Yeah, but because it's constantly shifting the event horizon, there are all sorts of perturbations around the surface. You're probably not going to see light.
So I would say technically it's an unstable orbit, literally unstable, meaning a slight perturbation, and it's either going to fall into the black hole or escape out. And so the things like the International Space Station are on very stable orbits. You perturb them and they kind of tend to rock back to that very stable point. This is more like sitting on the top of a mountain. It's anything, disturbs it slightly, it will fall into the black hole or come out. So you don't, but you do see things like rings, and you talked about gravitational lensing. Gravitational lensing is just the idea that there's a mass. It doesn't have to be spherical, it can be some crazy lumpy collection of galaxies or some other density. And you will see light shining from behind it will come around and you'll see it get lensed. And what you mean by that is it's bending the path of the light. It's just another language to describe the curved space-time. And you can see like entire arcs and things and really interesting geometric properties of the what's happening to the lensed light. nobody's ever seen what we call the light ring. That's what that unstable photon orbit is called, the light ring. I mean, we haven't seen that yet, but it's around what people are looking at when they take the picture of the black hole recently in the past. That's just very recently. Was that 2019? Because I remember, I think it was the centenary of the Eddington eclipse expedition, and it uses the same technology, which is to take the bending of light and to try to look for the light around a black hole that way. So we see effects that are very close in now. But I just want to address one question, which you said about the changing black hole. So some black holes are creating a lot of material and changing all the time, but some are not. Some black holes are just out there by themselves. They're not harming anybody. Nothing's happening to them. They're not doing anything to anybody else. We don't see them if they don't do something. So I just literally have a dark. So the idea that light can't escape literally just means they go dark. I can see a shadow because it'll absorb all the light within the event horizon and allow you to see the light coming from outside. It's no different than the shadow of a tree. That shadow is really quite harmless, but we can try to look for the shadow, and that's what this Event Horizon Telescope did, is it took a picture of the shadow, essentially, of the event horizon. But some black holes are just dark against a dark sky. There's nothing to look at. And that's why detecting the collisions of those black holes by the ringing of space-time with the gravitational wave experiments was so thrilling, because you're detecting black holes that are otherwise completely dark.
Thank you very much for clarifying my comment. Let me, though, ask or probe a bit further about this. I'm guessing that it is supermassive black holes at the center of galaxies that are, you can kind of count on them to be a center of a lot of activity, but then maybe stars that went supernova and then were ejected maybe by their solar system, or they already consumed everything around them and they're just kind of floating out there. They're the ones that they've got nothing going on.
Yeah, so there are a lot of star systems are born in pairs. There's a lot more binary star systems than there are single star systems. So we're kind of odd in that we just have our one sun. Not that odd, but Jupiter's almost a star. And so a lot of them are like, yeah, it could, I mean, it's not igniting, it's not burning thermonuclear fuel, but it's pretty big. And so it's not uncommon to have that, two largish body, two that actually burn thermonuclear fuel, or two stars. And if one of them dies as a black hole, it goes through its whole life cycle, it runs out of thermonuclear fuel, it begins to collapse, because it's the thermonuclear reactions that are pushing the star outward and keeping this incredibly massive body from collapsing. And when that fuel turns off, it can be a very catastrophic event. And if it's massive enough, it will just completely collapse to a black hole. Might supernova in between. So it bounces, explodes out, a big outer atmosphere, becomes the brightest thing in the galaxy for a while. But the core, the remnant that's left after that supernova explosion, if it's massive enough, it will form a black hole. And those can be very bright because they can start to cannibalize their companions. So this neighboring star that they were just living and orbiting, much more complex orbit, it's hard to know if planets could exist stably around the binary star systems. But now you have this black hole, and it starts to, like cotton candy, it starts to tear off tufts of the other star, and that gets really bright. And that was the first indirect evidence of black holes that we saw, was this kind of X-ray energy coming out of this very, very tiny, tiny region of space. So if you estimated how much mass is in this tiny region of space, you deduced indirectly that you must have a black hole causing all that mayhem. And eventually it just completely cannibalizes its companion.
Yeah, intergalactic cannibalism.
Yeah.
Very exciting.
Yes,
phenomenon.
very exciting, right? But if it's not a binary star system, it's just a massive star by itself, it'll go dark. And if they both become black holes, which is what we definitely now can detect, these binary black hole systems, they're in orbit around each other, they're totally dark. There's just no light coming out.